Hello, my name is Aveline Riddell, and with me is my co-presenter, James Riddell. We are going to be giving a presentation on self-attention and transformers. This presentation was originally prepared for a computer science course at the University of Waterloo, where we're both graduate students, and the course was given by Professor Wenhu Chen. All right, with that, let's get started. So the goal for this presentation is to talk about what attention looked like before the transformer architecture was introduced. In particular, this attention mechanism was highly coupled with an RNN structure, so we'll go over that. Then we'll shift to the Attention is All You Need paper that radically changed this field of study, where they decoupled this from RNNs, introduced the transformer architecture, and had quite an impact with their paper. We'll also touch on transformers in other domains, in particular the early adoption of transformers in computer vision, and the goal is to tackle some misconceptions along the way. So the notion of exploiting context in machine learning and deep learning isn't new. So with CNNs, these exploit context from spatial locality, and this is particularly useful for images, right? Where regions around a patch in an image give context for that particular patch. With RNNs, context is exploited from temporal locality, and this is useful for sequences or time series data. But the way these work, and the way that context is exploited is through the embedding of priors into the model, and this forces them to pay attention to relevant features for a given problem. And that given problem, again, is highly tied to the architecture and the way that these priors are embedded. What we now call self-attention in deep learning is, again, still this idea of paying attention to the most relevant parts or information or important parts of an input at a given time step, but without these embedded priors. And ideally, we'd like to learn what to pay attention to. This is very, very useful for sequence-to-sequence modeling. Now, the attention mechanism typically refers to a function that allows a model to attend to different context and content. And like I said before, ideally, we'd like to learn this. So what we're learning here is this attention functions, or the parameters of this function. Now, there's different ways that we can calculate attention. It can be additive or multiplicative, like with a dot product. And we can also, we have different names to distinguish attention based on what is being attended to. So for self-attention, content is being attended to itself. We typically refer to this as intra-attention as well. With cross-attention, content is attended to different content. We often refer to this as encoder-decoder attention or inter-attention. Now, we'll talk about these, the ways to calculate attention and the different types of attention a little bit more later on. But this gives you a high-level overview of the different terminologies used when talking about attention. So like I said earlier, the attention function or attention mechanism is really useful for sequence-to-sequence modeling. So what this means is, when we're talking about sequence-to-sequence modeling, the goal is to take an input sequence, X, and produce a meaningful sequence, Y, or an output sequence, Y. Now, this could look like text-to-text, where the input sequence is text and the output sequence is text. Think of tasks like question answering, translation, or text summarization. Now, this input sequence doesn't have to be text. It could also be an image. Think of image captioning, where we take an image and produce a caption, which embodies the output sequence. Now, we don't just go from the input sequence to the output sequence with some sort of magical black box. Often we use encoder-decoder models. The way that this works is the input sequence is encoded by an encoder, which then shares a state and a context vector, which captures the information and all the context from the input sequence, shares that with the decoder, which then meaningfully decodes this information to produce an output sequence. And it all depends on what the task is, of course, and what these sequences are. And usually these encoder-decoder models are implemented using RNNs. These are highly useful for sequence-to-sequence modeling. And also the transformer architecture is a type of encoder-decoder model useful for these types of tasks. And of course, we'll cover that later. But first, we're going to start talking. We'll start first with an explanation of how RNNs can be used for sequence-to-sequence modeling. Here we have a paper from 2014 called Sequence-to-Sequence Learning with Neural Networks that does sequence-to-sequence modeling with RNNs using this encoder-decoder structure. The encoder and the decoder are both instantiated using an LSTM, which is a type of recurrent neural network. And the way this works is the encoder starts with the input sequence. Let's say for now, this input sequence has 4 tokens, x1, x2, x3, and x4. Using these input tokens, we calculate the hidden states of the encoder. Now, for each token, we calculate its corresponding hidden state. So let's say for token x2, we calculate hidden state 2, but it also requires the previous hidden state to inform that hidden state. So for H2, we use H1 to help inform what that hidden state looks like. And we do this for all of the hidden states and all of the tokens until we get to the end of the sequence. But notice here, when we're calculating H4, we require the previous hidden state and the one before that and the one before that. So we end up with these dependencies where whatever the previous tokens and those hidden states were inform what the next hidden states are. But as these sequences get longer, this information gets watered down. And again, remember, RNNs use spatial locality as an embedded prior, right? Where the hidden states or the tokens closest to a hidden state or token have the most impact, have the biggest effect. But long-range dependencies, so inputs or tokens that happen earlier in the sequence, don't have as much impact anymore. Now, the way that this progresses now is once this token has been encoded, or these tokens, this input sequence has been encoded, the last hidden state is used to calculate a context vector and an initial state for the decoder. The context vector captures the information from the input sequence. From there, we do a very similar process where we use previous hidden state and the previous output token to calculate the next output token. So we do this in a recurrent, autoregressive fashion. Recurrent in this case because, again, we use the previous hidden state to calculate the next one. We do this for each output token that we're generating until we've arrived at an output sequence. Now, again, a hidden state is informed by, of course, its previous output token, but also all the hidden states that come before it. Again, it's this notion of leveraging spatial locality, which is that embedded prior that the RNN exploits. But we see that, again, whatever happened earlier in the sequence for the output gets watered down as we get further and further in the sequence. Now, another issue that we see is this context vector is reused for every hidden state of the decoder. We just use a single context vector that's supposed to capture all of the information from the inputs. But this tends to result in an informational bottleneck because of this fixed length context vector. The problem here is that if our inputs get really long, this context vector might not be able to capture all the information, but more importantly, as we're generating new output tokens, certain parts of the input might be more relevant or might be more important, and this context vector, the single context vector, might not capture that. So another paper from 2015 called Neural Machine Translation by Jointly Learning to Align and Translate addressed this informational bottleneck. they introduced the idea of using a different context vector for each time step in the decoder. So the process is very similar, but instead of using that single context vector that's used for each decoder hidden state, we're going to calculate a new one for each decoder hidden state, and we can craft it so that it looks at or captures the most important parts of the input sequence for that time step. So the way we do this is we still have the same setup, right, where we encode, produce an initial state for the decoder, but instead of just calculating a single context vector that's going to be used at every step of the decoder, we're calculating a new one. So how this works is we calculate first the alignment between each hidden state of the encoder with the previous decoder state. So in this case, for S1, to calculate context vector 1, we need that previous hidden state, in this case, S0. So we calculate the alignment scores using an attention function. Now, for now, let's keep this abstract. We'll get to what this looks like later, but it calculates the alignment or the compatibility between the hidden states and that decoder state. We then normalize these alignment scores to produce the attention weights, and then we calculate a weighted sum. So what's going on here is we use the attention weights to say how much of each hidden state are we going to use to inform what this context vector is. So that way we're saying, okay, hidden states with high attention weights are weighted higher, so they will have more impact when we go to calculate this next hidden state, and therefore that next output token. So essentially what these attention weights mean is, or represent, is they represent the measure that the target word, in this case Y1, is aligned to or translated from a source word, Xi, which is correspondent with each hidden state HI. It also reflects the importance of the annotation, therefore, the hidden states, with respect to the previous hidden state, right? Because we're using the previous hidden state and all of the different annotation vectors or hidden states of the encoder to calculate that context vector and generate the next output token. So we do this for each step or each hidden state of the decoder. We calculate a new context vector using the previous hidden state of the decoder and the previous output token generated by the decoder to inform what the next hidden state and the next output token are going to be. So this is our recurrent autoregressive process in which we do this. So what we've done is we've solved the issue now of capturing the most important parts of the input for generating each token in the output. Now, one thing we haven't really solved, though, is the fact that the recurrent structure of this, right, as our decoder produces more and more output tokens, and each previous decoder state informs what the next decoder state is going to be, we still lose some information about what previous hidden states or output tokens were generated. Now, our encoder is bidirectional in this case, which allows for the annotation of each word to summarize both preceding and following words. So we get this back and forth information. We capture the most important parts of the input. So that part is solved with this attention mechanism. Now, all steps are differentiable, so we can back propagate through everything and update the model parameters. So to provide a visualization for these attention weights, the authors of this paper produced this visualization for the task of translation. In this case, we have an English sentence on top and a French sentence on the left-hand side. Here, the pixels are colored or pixelated with a brightness that corresponds to the attention weight. So the more bright, the higher the attention weight. What this means is that the model was paying attention to particular inputs when generating an output token. So let's look at the word agreement. When the model was producing the word agreement in French, accord, it was paying attention to the word agreement in the English sentence. And so that's why we see a highly pixelated or bright pixel here in this visualization. So when we see a nice diagonal of bright pixels, it represents that there was a nice one-to-one correspondence of English to French words. Now, we don't see that everywhere, of course. This is usually due to either a different ordering of words that occur in different languages. So for example, European Economic Area, we see the diagonal the other direction because the French ordering of words is different, sort of inverted. Or we see some ambiguity that arises because of different semantic meanings of different words. For example, was, the word was in English, and a été in French, again, can represent different things, which means that the model was paying attention to other words as well when generating the words in French that represent the translated representation of those words in the English sentence. But it gives a nice idea for what the attention weights looks like, what the model was paying attention to when generating the outputs for this particular task. The authors compared their approach with the RNN and attention process with just a regular RNN encoder decoder structure. And they used two training paradigms, one with 30-word sentences and another with 50-word sentences. And what we see here is that the RNN with the attention mechanism built in on the 50-word training paradigm, we observe no performance degradation for longer sentence lengths. Now, this is because we made sure that the decoder knew what was important to pay attention to from the input. So we have a specialized context vector for each decoder time step when generating each new output token. Now, keep in mind that we're only looking at 50, 60 sentence lengths. So I'm sure we would probably still see some degradation as sentence lengths increase even more because we get that watered down effect in the decoder sequence. Now, a different paper from also 2015 called Show, Attend, and Tell, Neural Image Caption Generation with Visual Attention. They use this RNN with attention, but for a different task. They don't use a text input sequence, they use an image sequence for image captioning. It builds directly on this previous paper. And the way they do this is they have a very similar setup, but instead of using, the text as the input sequence, they take their image and extract the features using a convolutional neural network to produce the hidden states of the encoder. Essentially, these are feature vectors of the image that represent different image regions. So when we then go to generate the output sequence using the decoder, a new context vector is calculated for each decoder hidden state, and it attends to different image regions, right, which are captured by the feature vectors or the hidden states of the encoder. We still calculate the alignment scores, the attention weights, and then do that weighted sum that informs what the context vector is. And the idea here is that the attention weights indicate how much of the different regions of the image are important when generating that output token. Now, we do this still in an autoregressive recurrent fashion, right? Recurrent because we're using the previous decoder states to inform what the next decoder states are going to be and the next output tokens are going to be, but we're calculating a new context vector for each time step. All steps are differentiable, so we can backpropagate through everything and update model parameters. And each context vector, in this case, attends to different image regions. So it's telling the model, here, for this token, for this hidden state, we're paying attention to this region or that region to inform what that token should be for the output. Now, to give you a visualization, here it gives insight to where and what the attention focused on when generating each word. So here we still have this image of the bird. Let's look at when the model produced the word bird. At that time step, the model was paying attention to the region where the bird was. So that's how the model knew to produce the word bird for that region of the image. Now, if we go down and look further through the sequence where water was produced, at that point, the model was paying attention to the area around the bird where the water was. And so it makes sense that the word water was then produced by the model. Now, the paper, they introduced two ways of calculating attention. There's a deterministic soft attention, which is what I've explained to you so far. There's another way to do it, which they refer to as stochastic hard attention, which requires reinforcement learning. This is something you're interested in. I highly recommend you read the paper. It's beyond the scope for this presentation. Now, here's a couple more visualizations to really just reinforce this idea. Let's look at the first picture where a woman is throwing a frisbee. At the time where the model was paying attention to this region where the frisbee was, it produced the word frisbee in the caption. Okay, so we've talked now about how attention was incorporated into the encoder-decoder structure with RNNs. Now, in 2017, Vaswani and his colleagues published the Attention is All You Need paper. And this was a pretty radical paper at the time, and it still is. It's been very impactful and fundamental for a lot of AI technologies that we now know and use today. They decoupled attention from the RNN structure and introduced the transformer architecture. So let's dive right into that. But before we do it, I want to take a brief moment to talk to you about feature superposition and polysemanticity. So when we're working with deep neural networks, neural activations often do not represent a single thing. And this happens because neural networks want to represent more features than they have neurons for. And we see this with deep neural networks like the transformer architecture. With this, we observe that often many unrelated concepts are packed into single neurons. This results in the superposition of features. This is important because when we're talking about tokens and inputs and outputs to deep learning network layers or parts of those layers, it doesn't make sense to think of these inputs and outputs as tokens or words like we've been doing before. These tend to lose meaning as we get deeper and deeper into the network. Instead, we're going to be thinking of them as abstract or generic vectors, let's say. And again, this is due to this polysemanticity that arises with deep neural networks. Now, the unfortunate side effect of this is the decreased explainability in deep neural networks. There is some research being done in this area to add explainability back into deep neural networks like LLMs, which is being done by Anthropic. But for now, it's still quite an unsolved problem, and we just need to be careful when working with deep neural networks or talking or thinking about them, that we don't associate inputs and outputs with tangible things like words or tokens, because that's not what happens. It's because of the superposition and polysemanticity that occurs. Okay, with that in mind, let's move on and just I'm going to give a quick overview of the attention that we've seen so far. What we've seen so far is what we now refer to as additive recurrent attention. So additive because of the choice for the attention function, which in both cases that I've talked about before is a simple feed-forward network. It's an MLP network, and it's an additive calculation. The recurrent part of this attention mechanism is the fact that we need the previous decoder hidden state to calculate the next one, right? In this case, this image, the ST-1 is the previous decoder hidden state. We calculate the alignment of this hidden state with all of the encoder hidden state, the H's, to then inform what the context vector is, to then produce the next decoder hidden state. So this is this recurrent notion of we need the previous to produce the next. Now, there's some issues with this recurrent structure. The first is the scalability issue with this. Performance degrades as the distance between words increases. Now, we talked already about that context vector bottleneck that the attention mechanism addresses, right? We address this dilution of information from the encoder that captures the information from the inputs to the decoder. But still, as we produce longer output sequences in the decoder, information from earlier decoder hidden states and output tokens, these get watered down and diluted. And we see these long-range dependencies, and this is just why recurrent neural networks don't scale very well. We also have parallelization limitations. Recurrent processes lack the ability to be parallelized. There's really only so much we can parallelize because we need previous hidden states and previous output tokens to inform what the next hidden states and next output tokens are going to be. And then we have memory constraints. RNNs are notoriously known for having limited memory and struggle with those long-range dependencies. There's that diluted impact of earlier elements on output sequences as the sequence progresses. So how can we address these issues? Well, one way to do it is to decouple the attention from the RNN structure. We want to separate, the goal is to separate the attention mechanism into smaller, self-contained components that we can hopefully parallelize. Now remember that the attention is purely the act of determining the importance of elements to be passed forward in the model. We do this by calculating the attention weights, which lets the model pay attention to the most significant parts. And the goal for decoupling from RNNs is to produce a more general attention mechanism that's not confined to that recurrent structure. So we need a modified procedure. We still need to determine the weights based on the context that indicate the elements to attend to, and then we need to apply these weights to enhance attended features. Now, we're going to need a new set of notation for this because the notation that we've been using is highly coupled with the RNN structure, right? With hidden states and context vectors and all of that. What we're going to use instead is the key value query notation. And this is the notation also used in the Attention is All You Need paper. And it reinforces the notion that we're working with deep neural networks where we observe this superposition of features. So we're going to think of these keys, values, and queries and outputs as just generic or abstract vectors that we're not going to associate meaning to right now. So that's exactly what we're going to do for now, is just think of them as abstract vectors. Okay, so I've just drawn the attention mechanism here, but with a key value and query notation. So the idea here is we're going to find the alignment or compatibility of the keys, so the K's here, with a query. We calculate the alignment using an attention function. We saw before that we could do this using a feed-forward network, but there's multiple ways to do this. We're going to keep this just generic for now. Then these alignment scores are normalized to produce the attention weights. And then we use those attention weights, right, to scale the different values to produce an output vector. Now we can do this with multiple queries because we're trying to move away from this recurrent structure. where the previous query is not dependent on the next query, which is what it was with the RNN structure, right? Where these queries, so to speak, were the hidden states of the decoder. We're moving away from that. So we can calculate the queries and keys potentially at the same time, as long as we set our attention function up correctly or in a way that can leverage this. So here, the goal again is still to find the alignment or compatibility between keys and queries to scale the values. And now we're producing 3 outputs that correspond to the 3 queries that we're doing. Now at this point, let's talk about where those keys, values, and queries are coming from. And this is where the terms self-attention and cross-attention come in. For self-attention, keys, values, and queries are all derived from the same source. So an arbitrary input X, let's say, that goes through an arbitrary transformation to produce these keys, values, and queries. Now for cross-attention, the keys and values come from one source, and the queries are derived from a separate source. Now, it doesn't matter where they come from because they are all then passed into the attention function, which is agnostic to what the keys, values, and queries are or where they come from. But this is where this notion of self-attention and cross-attention comes from, as in it indicates the separation of the sources for the keys, values, and the queries. Now, in terms of implementation of this decoupled attention mechanism, the attention is all you need implemented it with 2 properties. The first is the choice for the attention function, which was the scaled dot product. Now, this is a good representation of compatibility. It's fast and it's interpretable. It's also parallelizable across all queries. So so we can leverage GPUs. We also scale this dot product for stable softmax gradients in high dimensions. Now, the other property is a common dimension for keys, values, and queries. Now, this is a requirement for the dot product. We can't dot product 2 vectors of different sizes, but it also simplifies architecture, the transformer architecture, which we'll talk about later, with predictable attention output shapes, and it just provides more consistent hidden state dimensions for easier model analysis. So now back to this attention diagram. We've added in these 2 properties. First is we see the shared dimension for the keys, values, and queries, as well as the output vector O. And we've now specified the choice for the attention function, which is the dot product between each query and each key scaled by the square root of the shared dimension, dk. Now we can calculate these dot products in parallel with matrix multiplications. So we can group all the keys into a matrix K, group all the queries into a matrix Q, and simply do a matrix multiplication, because this is doing the exact same thing as doing a dot product between each key and each query. We can do the same thing for the values and put all of the attention weights also in a matrix. So we can do another matrix multiplication to produce the matrix O, the outputs. Now, the reason that this is really useful is because it's highly concurrent on modern hardware, and we independently calculate each query.
Hi, so I'm going to take over from Aveline to do the next portion of this presentation. I'm going to talk to you really quickly about the multi-head attention, which builds on the mechanism Aveline just explained. I'll then go into a little bit of a talk about what transformers are doing and what that architecture looks like. We'll then progress into a little bit more of an implementational focus and take you through how you might implement a transformer yourself. And then hopefully throughout this process, I'd like to clear up some misconceptions about the transformer that come up colloquially just because of people's understanding about the notation and how it's presented commonly. So with that said, I'm going to jump into the first misconception that arises about transformers. And this has to do with the attention mechanism Aveline just outlined. So this is a misconception about what transformers are doing. And there's this common idea that because of the terminology, that being queries, keys, and values, people think that this is doing some sort of vector similarity search, right? Um, and because this notation is very convenient, a lot of people will have reference for what a database might do, or a dictionary where you look up something that is similar and then grab the corresponding value. People get overly attached to this, and it's really great to introduce users to the notion of, I guess, a similarity inner product using this definition. That being said, people don't know how to look past it, and this arises with the issue of people not understanding where we're getting our values from, and then what this transformer or attention mechanism, when we go about learning it, is actually learning. So the question arises, are we learning something that is parametric, where the meaning is distilled into a preset number of parameters or weights? Or is it non-parametric, like you'd see with a database, where you're just storing embedded representations that you can then look into? What I'm going to tell you is that the transformer is a parametric process through and through. There are systems or further implementations that have been proposed, like RAG, where you augment the transformer process by retrieving information that kind of muddies this, and they actually do use dictionaries to grab that information. But for today, we're just talking about the transformer in its vanilla format. And in this situation, we are just learning parametrically. So talking about what is being learned, Aveline has mentioned that the attention mechanism that Vaswani and his colleagues put forwards is this scaled dot product attention. But when we look at this, no matter where we're coming from, whether that's self-attention, where you're getting everything from a single input where you're attending to yourself, or cross-attention, where you have an arbitrary input attending to another input to generate like the queries, keys, and values. Regardless of this, the dot product attention is just an operation. It's not learning any parameters as part of that, which means we need to look elsewhere to try to figure out what we're going to be learning. And this is where the real power of the transformer comes in, is we want to learn linear maps or weights matrices that are going to take our arbitrary input, no matter where it's coming from, and transform that into the independent parts that will feed into this attention mechanism. Those are the queries, the keys, and the values. So to produce the queries, let's look at the self-attention example. We have our input X, which again, since we've got this polysemanticity of the representations in a deep neural network, we're just going to consider it an arbitrary vector or an arbitrary sequence of vectors in the situation where we look at all of X. And what we do is we multiply that with a weights matrix. And these are parameters that we're learning for the network that'll make us produce queries that are useful to then grab the relevant information. We likewise do this to inform what the keys are. And again, we're looking at that similarity between the keys and queries, and we want those to be distinct depending on what needs to be attended to. And then finally, the values. So when we're actually talking about attention, a lot of times because this notation is overloaded, and you'll see the multi-head attention that we'll talk about in a couple slides takes in keys, queries, values, but the attention mechanism it calls also takes in keys, values, and queries. Because they're overloaded so much, people think, well, the input in this situation is the exact same as the value. So if you have a query and a value, they could be the same. But while they could theoretically, when you're actually learning this through the process of optimization, these weights matrices are going to learn different things. So our keys and queries will be aligned, yes. But when we talk about self-attention, it's not just doing a attention between its input and itself. These are independent, or sorry, they are dependent on one another because they come from the same source, but they have been learned to have different representations that can then ask each other questions of, are you an important feature that I want to be using to carry that information forwards? So now that we have a little bit more intuition about where our values are coming from, where our keys and queries are also coming from, and we've talked about what is being learned in this process, I'm going to move into the idea of multi-head attention, which builds on top of that original attention. And it's what the paper really leverages to get this increased performance. So as I've mentioned a couple of times, it builds on top of the scaled dot product attention that the authors implement. It's an extension of this generalized attention mechanism outlined previously in our presentation. And the real idea here is that it's going to leverage multiple heads to attend to different things. So like we saw with the recurrent neural network situation earlier, having a singular context that only takes one perspective about what is important, even if we're doing it each time, which we've kind of introduced with this attention mechanism, is still an informational bottleneck. So even though we've gotten better because we've introduced attention, we can make it even better than that by having different sub-representations. And I'll get into how we learn these different representations in a minute. But the main idea is if we can look at the data from different angles, we can have the model learn to jointly attend to different views of that data, so that when we have the decoder finally go to access that information, it can take on a view and be comfortable that that information is there, that it needs to decode the next token or element of the arbitrary sequence. So I'm going to give a little bit of intuition for why multi-head attention is even needed in the first place. When we go through the top half of the attention block, so where we're talking about taking the attention weights and multiplying it with the values, what you'll notice is because we're doing this as a multiplication and addition, or a matrix multiplication when you put everything together and parallelize it, we multiply the values, but then we sum through the dimension of the values. So this is corresponding with the keys and the actual values themselves. So from one sequence, we're summing through based on a singular view. And since we sum through, we've lost resolution about what is important. Essentially, we've committed to one perspective. And the goal with multi-head attention is to learn multiple sets of weights. So we have one attention head that has one set of weights to produce the keys, values, and queries given an input, and then another head that has a different separate set of weights to learn a different set of queries, keys, and values, et cetera, et cetera. The paper actually extends this to learn 8 separate heads, and modern architectures that use the transformer have much, much, much more number of heads. And the real goal here is to learn sub-representations that give you different perspectives on the data, so we can learn a richer representation and pack all that context together about how each element in a sequence relates to the other elements in that sequence, regardless of if this is the input sequence that has a direct meaning from the tokens, or if we're further up in the network and dealing with just arbitrary sequences that have positional information or semantic or grammatical information packed into it. So you might ask yourself, well, if we're going to add a whole bunch of different attention heads, aren't we going to increase the computational cost dramatically? And you'd be correct if we didn't take extra precautions. Now, what the authors find as a kind of compromise to this is if they shrink the dimension of the sub-representation, so we go down to a smaller dimensional space for each attention head, we can reduce or compress the information given a certain lens to make it more useful for that perspective, but have lower computational cost. And what they find is if they divide the total dimension of the model, since we have that imposed fixed dimension that Aveline mentioned earlier, by the number of heads, we end up with a smaller dimensional subspace that still lets us compute in roughly the same amount of time as if we had a single head, but we can get a lot more rich information just because that compression isn't actually by that big of a factor. So a visual representation of what happens here is, say we have some source that's going to flow into our weights matrices, and I haven't rendered that on the slide here, but just imagine it's coming from the left. It would then flow through these weight matrices that are for each head, produce the keys, values, and queries, and then out of that, each attention head will produce a separate output matrix. And this is going to represent it's going to be dimension of T by dk, T referring to the number of elements in the decoding sequence, or where the queries are coming from in the first place. Now, if you recall that we have this constant imposed dimensionality of the model, you might look at the fact that we have multiple outputs now and say, well, that's not going to fly with our understanding that the model has consistent dimension throughout it. We need something that the rest of the model is set up to use and understand. So you'd be correct in that assumption. And what we finally want to do is introduce a final weights matrix that is also learned as a set of parameters to kind of pack up that rich amount of context from all these different views into the problem into a singular output. So we concatenate all of the heads and then do a matrix multiplication of that finally with this weight 0 or weight O, which represents the weights for this output transformation. And it's going to bring us back to that proper dimension of the model. So from dk times the number of heads to the D model. So we've talked now about multi-head attention, and that's kind of the understanding that we've just went through and why it's so important. Now I want to talk about how the transformer architecture uses that to escape the problems that RNNs had. So I'm going to say that the attention architecture in the transformer, this multi-head idea, is leveraged in 3 different ways in the transformer. One is it does self-attention in the encoder. The next is that it does masked self-attention in the decoder. And finally, we have that autoregressive element where we're doing the encoder-decoder cross-attention. Because we're going through the process of decoding a sequence and we need to produce token at a time, we do end up with this autoregressive element that's still there. But the goal is to use these new self-attention elements that I'll explain a little bit more in a second to offload a lot of that work so that the computer can run it in parallel and we do the minimal amount of time as possible, kind of going from one sequence to the next sequence, or from one element of the sequence to the next element. So recall that we've got a custom context per layer. So we've got different heads per layer of the architecture, and we want to reduce the amount of time that's going into that. So what you might say is, whereas the recurrent neural network architecture needs the previous input and we run all of them in sequence, instead, let's take away the idea of this recurrence. Instead, we're going to run the idea of self-attention on the entire input that we're looking at. So at a given time step, the history of the model, the tokens that have already been seen, are then encoded as part of this self-attention block, and it allows the model to jointly attend to all positions of the encoder. So it doesn't need to just flow through a path of the previous hidden states, but each area, because we add in a little bit of positional information at the very start, can then look at all of the other elements and understand how it relates to the other context that's there. And this embeds context about how the elements not only relate to one another, but then can be useful downstream. So each layer is, or each attention block is optimized so that it's feeding forward in the network the most important information. Now, the mass self-attention in the decoder also eliminates this idea of dependency on the previous tokens as part of the architecture. We still have this autoregressive process, but at any single iteration of that autoregressive process, we're running with all of the previously decoded tokens. And instead of needing to do a complex path traversal to get that information, we treat it the exact same way as the self-attention in the encoder. So we have each element look at everything else that was previously there to try to inform, well, what is the context that I need to share to generate this token, right? And at this point, since we've decoupled from the recurrent structure, we're just talking about the next token that would be produced as if it was a single output. Now, this comes up with an issue of forward-looking bias because certain elements weren't produced at the time that they would be actually seen, right? As you go from left to right in an encoded sequence, or a sequence that you're trying to decode, by the time you get to token 3, you have not seen the information or context about token 4, 5, etc. So you don't want those impacting how it makes its embedding. So in this situation, what we do is the authors introduce a notion of masking or contextual masking that blocks out the future so that you can't inform the important information that you're going to express based off of future information. And what this allows us to do is still do this in parallel because we've got the entire sequence at once, and all of the queries that the model will be seeing are able to be independent of one another because the architecture doesn't force them to have that recurrent structure. And that's the real strength of what's going on here, is we've offloaded a lot of that work, even though we have to do this autoregressively, to the self-attention part. Finally, we have the encoder-decoder cross-attention. And what this is going to allow us to do is have our decoder look at the information from the encoder and extract and pull in the relevant context to inform how it's going to continue decoding. So we still have that encoder that's going to take all the information and compress it into useful context in a latent space, and then the decoder that's going to exploit that. But the area between the two where we're actually doing calculations autoregressively is minimized. And that's the real essence of why the transformer is so much more efficient. So the authors further motivate this with kind of a why self-attention section. If I was to summarize it quickly, they break their analysis down into 3 components. One is the complexity per layer. One is the sequential number of operations that needed to be run. And the final one is the maximum path length. So working right to left, I'm going to talk about the maximum path length first. This comes from the notion of the recurrent neural network, where to get information about your hidden state from your dependencies, you actually needed to flow through the previous hidden states. So at any single time, your time complexity is based on how long that path is, or the number of elements you've seen. In the self-attention block, because we've encoded that understanding of position into it, and our architecture doesn't enforce any type of dependency here, we don't need to go looking for that information elsewhere. It will be encoded into the position that I'm actually referring to at the time of doing the calculation. So the maximum path length is considered constant. As far as sequential operations go, this is just referring to how much can be parallelized. So again, because we've removed that recurrent operation, even though we're doing it iteration by iteration, at a single iteration, it's a fixed or constant time because I'm not dependent on flowing through the model state at a time. Finally, we have the complexity per layer. And for self-attention, since we've talked about this at length as a scale dot product that we can then use as a matrix multiplication, we end up with a time complexity of n squared d, just because we're doing these matrix multiplications per iteration through the network. And this is per layer. So that explains what's going on here. And what we notice is that the self-attention mechanism on modern hardware, where we can really use that concurrency that's been so optimized for doing matrix multiplications, we end up with a lower computational complexity, a greater amount of the computation that can actually be parallelized, and we end up with a representation that encodes the positional and referential information about each element with relationship to each other in the sequence. So this just emphasizes the idea that this is much cheaper. And when things are cheaper, we actually have the ability for the same cost to go deeper, which will allow us to be more powerful given a fixed number of parameters. It's also faster to train because we have the ability, we don't have that recurrent relationship. So when we're going through a training process, we don't need to iteratively predict each token in a row. You can take a single sequence and just phrase it as predict the next token and batch up based on, okay, given this input, predict the single next token. And you can run all of those in parallel. Finally, as a little bit of conversation, when the vocabulary that you're trying to express or the sequence length, n, for a given input that you're trying to turn into another sequence is smaller than the actual dimension of your model. So the hidden representation state, which it often is when we're dealing with sequences, it's going to be much faster to use the self-attention mechanism than the recurrent one. So we also have the benefit just by nature of the problem that people are using this for. So now that we've motivated how the transformer is going to be using these elements of self-attention, I'm going to talk about the architecture a little bit. And this is going to be a high-level glance. We'll get into more of the implementation details down the road. But if you're going to take anything from this presentation, I want it to be the multi-head attention and why the transformer is able to decouple from the RNN and why that's a good thing. And also how they work together to build this overall transformer architecture. So when you hear about it in literature or presentations or just projects in general, you understand what's going on architecturally. So given this image that I've got on the screen, let's talk about what this task is. We're going from an arbitrary input sequence to an arbitrary decoded sequence or target sequence. And the idea is that for this model to work, we need to go to a floating point dimension system, right? These neural networks aren't designed to work on tokens or symbols explicitly. Instead, they use a numerical approach. So we're going to take our input and our output, because both of them are going to flow through these encoder and decoder stacks, and we're going to embed them into a numerical space, right? So this goes through an input embedding layer, let's say, and an output embedding layer to then flow into the rest of the model. Next, these sequences will go into the process of positional encoding. Now, the positional encoding element of this architecture is going to weave in or superimpose into the signal information about where the element is with reference to all the other elements. And this is why we're able to get rid of this recurrent relationship. We don't need the path to define what came before or what comes after, because that information is directly available in the representation of that element of the sequence. We then have that common encoder-decoder architecture that we talked about earlier, and we'll zoom in on these in a second. But the main idea is we're going to compress that information in the encoder, and then in the decoder, expand it out to generate that next token flowing through the prediction head or generator at the top. And that prediction head will output a set of probabilities about what the token could be in a preset vocal corporum or vocabulary that you're using to represent these sequences. And then that'll flow through a decoding procedure that'll select what the next token is given those probabilities. And that's the part that's autoregressive here, is that given a previous amount of decoded tokens, we're going to predict what the next token could be and use some decoding procedure to select the one that is most likely. So zooming in on the encoder block, The encoder is essentially going to be applying this self-attention to add on context about how the elements relate to one another. So in a language to language or text to text task, this is really adding in grammatical or sequential context to the representation itself as it flows through the model. And it's all about extracting features that have this superimposed context that's insanely powerful to allow the decoder to then get different perspectives into the data so that for every token, it can grab the context that is most important for it. The decoder, on the other hand, is going to have a similar process, but it's going to mask the self-attention so that we don't have that forward-looking bias. And it's going to have an additional cross-attention into the encoder to grab that information that's useful from before. Now, in both these situations, as we get further into the implementation, I'll talk about it, but we have a final feed-forward network that's added into these blocks. And what this feed-forward network is going to do is if the multi-head attention is adding context about what's important, the feed-forward network is going to allow us to exploit that context so that we can get a richer representation going forwards. So the multi-head attention says these things are the things you should be paying attention to. And the feed-forward network at any single situation is going to say, okay, based on this attention, this is what I want to be doing with my signal. Between all of these kind of sub-layers or sub-attention blocks, we have these connections, so these sub-layer connections, and I'll talk more about those in the future, but they're really there to regularize the signal and make sure that we don't have any problems with exploding or vanishing gradients, or we don't overfit the data that we've seen. The generator is a final head that's attached to the architecture. And it's very simple. It's going to take a linear layer, flow into a softmax, and that's going to produce based on the logics that the model produced. It's going to take that and transform them into output probabilities in the vocabulary that you're training. Now, as far as the decoding process goes, this is typically done greedily. So you just do kind of like an argmax. You take the most likely probability and just decode that directly as the next token. When you're training the model, we don't really deal with the decoded tokens. We always keep it in an encoded state. That way we can just continue to flow through the training process. As Aveline mentioned earlier, Vaswani and his colleagues use a fixed implementational, a dimensional implementation. So they use D model throughout the architecture, at least as far as what's handed between layers. And the reason for this is it's going to make it very easy to stack these blocks, so the encoder blocks and the decoder blocks, to achieve depth in our model. And the more parameters, the better the neural network is going to be at approximating whatever the task you're doing is. Now, I want to clear up real quick while I've got this diagram on screen, the notion of stacking transformer blocks. And I'll do this a little bit further when I clear up another misconception later on. But where you see this times n, this is referring to that actual block itself. So when we stack encoder blocks, it's going to be an encoder on top of another encoder and a decoder on top of another decoder. The paper that the authors produced themselves used 6 stacked encoder blocks and stacked decoder blocks. But as far as this figure goes, I think it can be a little bit misleading about what the times n means here. And you want to think of it as stacking the encoders and the decoders, not stacking full transformers. Okay, so with that out of the way, I want to go into a little bit of the implementational details. And I'm going to be leveraging the annotated transformer, which is an excellent resource. I've put the link down below on the slide to go through this as part of my explanation. And I encourage you to actually go and read this yourself. You'll have more time to look at the code and reflect on what that means with relationship to the actual paper, which they include snippets of, and essentially just walk through what the paper means step by step. So it's a great resource. For the presentation today, I want to treat building the transformer kind of like building a Lego house. We're going to start really small with little blocks and then build up different modules that we can then compose together and build out the final transformer architecture that you might use or implement in real life. And I'm going to present it in a slightly different order than what the annotated transformer does, because I think it fits the narrative that we're trying to display to you a little bit better. So if I was to go about building the Lego house that is this transformer, when we want to talk about this, it might be helpful so that you don't have a lot of repeated code to introduce some type of cloning or copying function. So if we design a subcomponent, say it's a wall of this hypothetical house, I want to be able to make a whole bunch of walls that look the same so that I can then use that to build the infrastructure, or in this situation, the architecture of the transformer. So The main motivation here is if we can repeat elements, we can then stack them deeper with no real design cost behind it. And like the VGG implementation, which was a computer vision implementation, not necessarily related to this, but they added this idea of having composable blocks that you can stack. So we want to be doing that with our transformers as well. So this function is going to be called clones, and essentially what it's going to do is, given a module, in this case we're doing this in PyTorch, create n copies of it. Now, whenever you're creating clones of something that has learned parameters in either PyTorch or TensorFlow, it's important that these, unless explicitly designed that way, these clones should not share the same parameters. And with the transformer, we want to make sure they're separate so that the different heads learn separate things, or that the different stacks learn, or different stacked blocks of the encoder or decoder are learning separate parameters. That way they have the full power of being able to optimize to that specific part of the network. So when we actually go to make this model, you need to remember at the very end to reinitialize all of the model parameters so that they're separate and independent per clone. Okay, so with that understood, let's build the first part of our architecture, our Lego house. And in this situation, we need to understand how we're going to get information into our transformer in the first place. So I mentioned earlier that we're going to use embeddings into kind of a numerical system of the input vocabulary. Now, if these are tokens, such as those associated with words, we essentially need to be able to take the independent parts or the individual parts of, say, a phrase like I am James, and break that up into little sub pieces that can then be turned into numerical vectors of fixed length that we can then feed into the model. And this is mainly because neural architectures, they work on numbers. Additionally, when you're dealing with a large possible vocabulary, like the entirety of the English language, or in modern large language models, maybe the entire vocabulary of all languages, we have a large number of words or symbols that represent or communicate meaning for that sequence. And we don't want our neural network to be extremely wide as far as the dimension goes, because it's going to be inefficient and take a long, long time to calculate each layer. So as part of this embedding process, a benefit of converting to this numerical system is we're going to reduce the dimensionality and make computation more efficient. Now, how we go about kind of building these embeddings is using a learned mapping. You can think of this like a standard linear projection that you'd have in a neural network, except instead of doing like a linear layer, we're going to have a dictionary that's going to look up or map to the vocabulary and have corresponding unique vectors. So we essentially learn weights that are going to go and do that lookup to find out what the corresponding word is. But it's still doing this linear layer. Once you've got it into the numerical space, we still do a linear layer to get it to that final embedding. Now, the next element of how we're going to get data into our transformer is the positional encoding. And what this is doing is it's going to add information about the element in the sequence's position with reference to the other elements. And we do this explicitly so that we can avoid the recurrence or convolutional structure, because when you're doing computation, the representation itself has that information kind of layered on top of it or interweaved with that signal. And how we can go about doing this is because we've produced a fixed dimensional embedded representation of the feature for the input sequence. Since it's fixed dimensional, we can actually do an element-wise addition to add in that positional element or information, as long as that positional information shares the same dimension with the embedded feature. So the authors go about this in a couple of ways. The one that they highlight in their paper is that they utilize the sinusoidal positional encoding. And they do this in favor of other approaches like a learned positional encoding using an MLP that they also experimented with, because the sinusoidal representation is, number one, a little bit more intuitive to understand. And number two, because sine waves have that repeating fashion and you can represent an offset from one position to another position as a linear function, they hypothesize that as context lengths get longer and longer, it'll allow the model to easily learn how to attend to relevant positions between different elements and possibly generalize to longer sequence lengths than they were trained on a little bit better. So as far as this goes, what they do is essentially interweave the cosine signal and a sine signal I've got the equations for these off to the side, where I is going to represent the position in the sequence, and L is going to be the I guess index into the dimension of the representation for that given element in the sequence. So the signal gets embedded into that representation of the element based on the index L, and then for each token in the sequence or each element in this arbitrary sequence, we're going to be adding in that positional information based on where it is or its index I. There are further works that have built on top of the transformer to kind of improve how we're getting this positional encoding. Rope is a great method that was produced after the fact and is highly used nowadays. I encourage you to kind of go and look at that up. If you're going to implement this yourself, it's important to understand where the foundation is, so what the original transformer paper used, and it's easy to wrap your head around what's happening where we're adding or embedding this positional encoding. But if you use a rotary positional encoding, which is more of a modern feature, you can get the same level of expressiveness, but without needing two separate signals. So it's something I'd encourage you to go and look at after. Nonetheless, the main idea is, as far as implementation goes, we're going to have some function that's going to add in that positional information to the actual feature representation that the model is going to take. So the information is going to be there. And if we look at our PyTorch code off to the side, you can see I've highlighted the element where we're computing the sine wave and the cos wave for each element. And then we just interleave them together and then do our linear projection. So or not linear projection, we're doing the in-place addition of that signal with the actual feature representation. So with that understood, we've talked about how we're going to get information into our model. And you keep in mind that this happens in the encoder, but also with the previously decoded tokens. So we also go through that embedding and positional encoding to get ready to go into the decoder layer. But once we've got information that's ready to be taken by this encoder-decoder structure, we need to talk about what the encoder-decoder structure actually looks like. So both the encoder-decoder, or the encoder and the decoder, have a number of sub-layers that are going to be useful for building out their structure. One of which is the multi-head attention sublayer. And this is going to carry out that multi-head attention, learning the weights that allow us to create keys, values, and queries like we talked about earlier. And the main idea behind this, like we've talked about earlier, is to extract the relevant context from an input sequence. And we leverage multiple heads to provide a greater resolution or different views into the problem so that that context is available from different angles. And how this is implemented is directly how we explained it earlier. If you want to look at a code representation of this, we're still using that scaled dot product implementation. So if we're doing just the attention here, and keep in mind that these are the keys, values, and queries after doing that linear projection, right? So this is just the attention function itself. We do our matrix multiplication of our query and our keys, scale it by the dimension dk. And then if you see at the very bottom here, we're then going to take the attention weights after normalizing through a softmax and multiply them by the values to extract how much of each value we're using or how much we need to attend to that. Now, there are a couple of useful things that you can build into your implementation when you're doing it. One is this idea of masking and the other is dropout. The main idea for incorporating these when you're designing your own implementation is it's going to speed up the ability to compose these models because you don't need to design a custom attention function for the encoder or a custom one for the decoder. Because we know the decoder is going to be using this masking, we can set it as a parameter of this function so that you can use the exact same attention function for both the encoder and decoder. The dropout here is just a benefit of our sublayer connections and in general, just a regularization strategy that we're going to use throughout the model. Dropout just essentially drops some random features inside of our representation so that our model doesn't tend to overfit to the data that it's seeing. So this is a form of implicit regularization that's a useful pattern to build into networks as you get deeper and deeper to avoid overfitting. Now, building on this attention function is the idea of the multi-head attention. Now, again, there's this ambiguity about what the multi-head attention's notation is. When we look at the forward pass here, where we're taking in a query, a key, and a value, I would name these something different, but the common implementations that are corresponding with the paper are going to name them the query, key, and value. Think of these as the actual signals themselves before they go through that linear projection that's going to take them to that other space, the sub-representation that is being learned. So in this situation, if we were doing self-attention, the query, key, and value would all be the same thing. And when we're doing a cross-attention implementation, the query would be from one source, the decoded sequence that we're decoding, and the key and value would come from a memory of what the encoded source looks like. Either way, I've highlighted the relevant parts here. Namely, we're going to go through, and because we've got this matrix multiplication and we want to accelerate this on modern hardware, we can build in this notion of batching to really take advantage of the self-attention and make it concurrent and fast. So if we do all of our linear projections at once, and that's what you see in this block with the comment that starts with the number 1, we're going to go through, carry out all of these projections, and it's going to let us get to the point where we can feed it into our attention mechanism, which follows right beneath it, very quickly and in parallel. We then go through the process of concatenating all of the different multiple attention heads. And then finally, at the very bottom, we do a linear projection using that learned weights matrix to take us back to the dimension of the model that we can feed into the rest of it. So this is really just taking us through that multi-head attention process that I explained earlier, but giving a little bit of an implementation detail here. You can see on the left-hand side where we're initializing the multi-head attention block or sublayer, that we are cloning the actual layers that are going to be used to learn the matrices or the parameters of the model. That way we can essentially, instead of needing to copy each one as a code block, we just copy the module itself to build out the 8 attention heads that this model is going to expect. Keeping in mind that we need to initialize all those values so that they're independent of one another before we start training. Okay, so with the first sublayer understood, I'm going to move into the second one, which is the position-wise feed-forward network. And what's happening here, or an intuition for it, is that it's going to apply a learned transformation to each position in the input representation, but they're applied separately and identically. So when we go through the multi-head attention, we're essentially going to convert our values dimension into our queries dimension, right? So we sum through the values per query. What we want to do with the position-wide feed-forward network is we've added in that context per query. We now want to per query, so keep that independence of each query lane, but now exploit that context. So we're going to blow it up, learn how to map it to something more useful, and then recompress it in dimension. So we want to exploit the context that's already been added by previous sublayers. And the main idea is that we're adding more parameters to the network so that it can approximate a greater complexity. And at the end of the day, a neural network is a universal approximator as you get deeper or wider arbitrarily. And the main idea is we want to learn how to go from one sequence to another sequence with the task of sequence translation. So the more parameters, the better your model will be, assuming it's been trained well. And then the main idea here, or how it's going about exploiting this context, is it's going to increase the resolution of each position momentarily to allow the model to simulate something that's got, or to exploit this superposition of context. So unravel it a little bit, do some computation, and then remap back to that fixed dimension of the model. So they do this through a linear MLP or a fully connected feed-forward network with ReLU activations in between. And the keynote is that the hidden space is going to have higher dimensionality. So I've drawn a picture off to the side just to explain this a little bit. When you've got the superposition of contexts, you might see that the positional nodes have different elements that are adding to the context. Now, because as you go deeper in neural networks, we kind of lose that discernible meaning. The meaning's still there, but there's a lot of contices that are wrapped up into a single node's representation. So it's hard to isolate that. So I've just come up with like some colors that I've assigned. You could think maybe one of them is about what the actual word's meaning was in an encoded sequence. Some of it is the relation to another element. Maybe the purple is relation to another element in the sequence or one of its neighbors. But the main idea is during this feed forward or the position-wise feed forward sublayer, we're going to blow up the dimension so that different parts of the features can represent different things. And then when we go and recombine that, we can recombine it in a different way that makes that context more accessible and more useful down the line. As far as an implementation goes, the feed forward part of this model is very simple. We're just going to have 2 linear layers that are stacked. We're going to add in some dropout to increase the ability to do regularization. And in a forward pass, we're just going to do 1 linear projection do our ReLU on it, then do the next linear projection. Perfect. And with that understood, we have the sub-blocks assembled, so these sub-layers. But how we go about connecting them is also important. So as far as the implementation goes, I went one slide too far. Here we go. So as far as the implementation goes, the transformer incorporates a sublayer connection between these sublayers, or surrounding each of the sublayers. And what this is going to do is add in that regularization, and I guess combat poor gradient behavior throughout the model. So this is just making it so that we can train stably, and we don't overfit to the data. They do this through 3 different mechanisms. One is a residual connection. The next is this dropout, which I've already explained, so I'll gloss over a little bit. And finally, they use a layer norm as part of the sublayer connection. And I've put the formula for what this is down below. So they do a layer norm on the original signal, which is what the residual connection is. Essentially, you only pass through in the model to represent a residual element, because it's a lot cheaper to learn a residual than it is to learn the entire signal. And add the original signal with that learned residual. And this preserves more of the original signal through this idea of a skip connection, so where you add X plus the thing you've learned. And it also alleviates some of the issues with vanishing gradient, because we aren't computing as much of a number. So the gradient doesn't have the problem of having too large of a number where it becomes poorly behaved. So in general, that's the residual connection. You see that that's wrapped in the layer norm in this situation. And what a layer norm is going to do is just scale down the values so that they're well behaved per layer, right? So based on all of the numbers that are in that single layer, we're going to scale them so that they're well behaved and we don't have vanishing or exploding gradients. As far as implementations go, I've put the layer norm off to the side because I think it's kind of interesting that this isn't the same as, say, like if you're doing a batch norm where you have an entire batch. It's not per batch, it's per layer in the situation. So we just essentially calculate the mean and the standard deviation and then normalize what that layer's activations look like based on that. And then the actual sublayer connection I've put a photo of down and off to the right. And this is the more important element. This is how we compose or add in all these different types of regularization to the connections between these sublayers. You see in the forward pass, we're just going to pass in the dropout on the sublayer on the layer normed version of the signal. And the sublayer itself is either that multi-head attention or the point position-wise feed-forward network. Now, you might notice that this is in a separate order than what the actual equation is that I put earlier. The equation is derived from the paper, and this is one area where the annotated transformers deviates from the source text a little bit. And they find it relatively the same, but a little bit cheaper when you're going through the process of applying or of learning this, to just reorder the steps of applying these regularizations in this fashion. When it comes time for your implementation, you can toy around a little bit with this. I prefer doing the implementation that the paper proposes because we have that layer norm on the signal plus the residual instead of just the residual component. So now we have all of the pieces that are needed to build the encoder and the decoder. So let's talk about the encoder first. So the encoder itself, or an encoder layer, is a composable block for the task of encoding an input sequence representation with this self-attention that we've talked about. So it's going to be taking in whatever the arbitrary input. Maybe it's the original signal, maybe it's one of the hidden states as we get deeper and deeper in this network, and carrying out the self-attention to layer in that context and the feed-forward network to exploit that context. So the main idea of why we want to compose it in this repeatable block with fixed input and output dimensions is it makes it very easy to construct our model. We can essentially stack these to get arbitrary depth, depending on how far we want to stack it. And it allows the encoder to have this repeated multi-head attention, which gives us more parameters and the ability to model more complex positional interactions just because by nature that we've gone a lot deeper. And we've had more time to extract a relationship and then say, okay, this is contributing this much. The next time that we abstract a layer further, we can say, well, that was contributing that much and another element was contributing this much. Together, when those contribute that much, this is what happens. So we can build in more complex, I guess, conditioning to the model just by going deep. And how we go about achieving this is implementing an encoder block with the sublayer connections. So we have the multi-head self-attention and then the feed forward with the sublayer connections between each of them. So as far as implementation goes, it's exactly what I've described. The key is that we create our clones of the sublayers so that we have multiple of them, and then we're just going to stack as many as we need. In this situation, we flow into the feed for or the multi-head self-attention first using this sublayer connection, and then from the output of that sublayer connection, we're going to flow into the feed forward where it's modeling the residual, and then the rest of the sublayer connection is going to pull through that rest of that signal, and then we can stack these arbitrarily deep. The decoder, on the other hand, is going to be very similar to the encoder, but we need that element of masking for the multi-head attention, so this causal masking that prevents you from seeing the future. And we need an additional sublayer that's going to be doing the exact same operation, except it's doing cross attention. So where we're getting the signal from is going to come from the encoder for the keys and values rather than the decoded sequence thus far. As far as motivation for why we want to do the masking, I think I've explained this a little bit previously, but the main idea is it's preventing cheating, where the model is, I guess, forward-looking in the output when it's trying to learn how to predict the next token. So if you're going through the training task and it could see the future data, the model might fit just to look at that next token. In fact, that's the best thing it could do to predict what the token should be, and it won't learn this causal relationship between previous tokens and what should flow next. So we shield it from that information so that it can purely attend to past context. As far as implementations go, we're going to have a very similar structure using those sublayer blocks that we talked about earlier, except what I've highlighted down below is with the self-attention that's masked, we go from X, 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 so from one sequence attending to itself with a mask that stops the future looking. And then the next layer where we're doing this cross attention, you'll notice that we have the queries coming from one source, but our keys and values are coming from this memory, which is it's coming from the attention to the encoder. So the encoded context that's gone through and been developed. Finally, that'll pass through the feed forward block to exploit that context again. And because we have this composable structure, we can stack them one on top of each other to exploit and leverage all of that context that we've intertwined into this polysemantic representation. So once we've established what the encoder blocks and decoder blocks look like, before we can assemble the actual encoder-decoder structure, encoder-decoder structure itself, we need to define the prediction head. As I described earlier, this is just the final thing that's going to take us to the output probabilities, and it's very simple. We do a linear layer to convert into logits, and then we're going to throw through a softmax to produce the probabilities for what the next token should be. And this is going to map us back to the vocabulary corpora that the actual tokens are from. So in an image space, these would be the patches of an image. Where we're talking about a text space, these would be the tokens that the sequence holds. Implementation is very straightforward. If you want, you can pause the presentation at this time and look at that. I'm just going to keep going to the actual assembly of the encoder-decoder structure. And I think this is where it's important to talk about what's going on and clear up a misconception. So I'll give you the picture here real quick. We essentially stack a whole bunch of the encoder blocks on top of each other and a whole bunch of the decoder blocks on top of each other. We then flow into that generator to produce our most likely probabilities for what the next token should be. And then we know down the line that's going to flow into that decoding process that's actually going to produce that token. Implementation-wise, this is very simple. We're just going to use that clones. We're going to exploit that clones helper function that we made to create copies of the encoder and decoder blocks. We're going to stack them on top of each other. And then when it comes time to predict, you see in the forward pass, we just go through the number of blocks. They call them layers in their implementation here, but we're just going to do signal into the first encoder block, take that output, put it into the next decoder block, and so on. Or encoder goes into encoder, decoders flow into the decoders using that learned memory from the encoder as well. And this brings us to that misconception about transformers. And this really, I believe, originated because of that figure that I keep showing with the times n. and it's an incorrect understanding of what it means to stack layers. So the notion of a whole transformer block being stacked on top of each other is incorrect, and the main reason is that where an encoder flowing into the decoder for the cross attention, one might think you just stack them on top of each other. You then don't get to exploit in the later layers of the decoder, the earlier layers of the decoder, sorry, the rich context that's been accumulated throughout the encoder. So rather than having an encoder flow into the decoder and then the output of that decoder flow into the next block or something like that, when we talk about stacking transformers, we're talking about either stacking the encoders themselves to build a more rich representation with the relational context embedded in the signal, or we're talking about stacking the decoders to do the same thing, maybe do some masked or some cross attention to grab information from somewhere else. But the main idea is we want to be doing that self-attention and building a comprehensive representation through the signal, but with the purpose of producing a token in that case. So when we talk about stacking transformers, it's stacking all of the encoders, producing a single representation that has multiple bits of context about different ways you could view the problem. So the decoder does have a rich representation it can query into. And then after having each decoder stacked on top of each other where they flow, that they all grab information during the cross attention from the final output of the final encoder block. And this is exactly what we do when we assemble the encoder decoder. We build our encoder by stacking the encoder blocks, the decoder by stacking the decoder blocks. We throw a generator on top and we put it all together to get this encoder decoder, where inputs will flow in through the encoder that we see inside of the encode process. And in the forward process, we can see we're calling the encode on the source. And then that output will flow into the decoder process as the memory, along with the previously decoded sequence. Putting that all together, we get this architecture that is highly parallelizable. And then to move from one iteration to another, we just decode autoregressively by predicting the next token and then appending that to the previously decoded list and continuing in that process. Here's a final implementation for actually making this model. The most important part is at the very bottom here, where we make sure we go through the process of independently initializing all of the parameters in the model. Since we've used this clone helper function so pervasively, we want to make sure that we don't accidentally have shared parameters that are trying to learn too many tasks or converging to one modality of prediction. And with that, we've gone through the implementation of the transformer from the ground up, kind of assembling out the architecture like a Lego house. I'm now going to talk briefly about training transformers. The notion of a model, I think, is incomplete if we just talk about architecture. Like with people, where nature and nurture both play a role in how we express and evolve in our world, models are a product of both their architecture, so the structure that they have, and how they were trained. So the training influences how the parameters in the model are expressed or what they have learned. This comes to the notion of garbage in, garbage out. If you go through a terrible training process, no matter how good your architecture is, your model is going to underperform because the model at the end of the day, or the architecture, is fitting to the training data through this training process. So if a transformer architecture, which we know has the ability to attend bidirectionally through the self-attention to all elements in a sequence, if it is shown examples that encourage bidirectional attention, it will learn that. And subsequent papers like BERT use large-scale pre-training to learn and encourage that bidirectional expression of the transformer parameters. But on the alternative side, if it's shown examples that only require rightward-looking attention, so that causal attention where you are looking at the past only, it may express more unidirectional behavior and it won't generalize as well. So this is just a quick synopsis of the fact that when we have a transformer architecture, we want to make sure we go through a good training procedure. But what Vaswani and his colleagues do in the paper is they train using masked attention. So they build out this attention mechanism that can prevent forward-looking bias, where they give a set of pre-tokens and they want to predict an output target token based on only the previous inputs. And how they do this at a large scale is they batch up all of the training jobs by just saying, this is what you can see in a previous window, and this is the single token you're trying to predict. So that for a full sequence, you don't need to run through iterating generating the first one, then the second token, then the third token, etc. You can just, given some finite window of the past, predict what the next token would be. And you can essentially build a sliding window over all the data and train on all windows and all targets at the same time. So we've talked about this a little bit. How it's actually implemented is creating a subsequent mask, or this causal mask. This is done by just saying, for a window, so let's say we are at token 4, I can see tokens 3, 2, 1, and 0, but none of the future. So that's what the figure off to the side shows. We can generate that mask, and because we've baked in the parameter of a mask to our attention function, it's actually really easy to implement this and use it. So we pass in the subsequent mask to our mask self-attention in the decoder block when we're training, and we make sure that it can only see the past. Now, when we're handing this in, how the authors apply this masking is they do it before the softmax, but because the softmax is going to be going and normalizing to convert this to a probability, we need to set the number as negatively as we can. So the authors do -1 to the power of -9, which is a very negative number. So when it goes through the softmax for these keys and queries, the stuff that we shouldn't be seeing, the keys and queries, when we're referring to the keys that the query shouldn't have the information from, the values of them are going to be so negative that it becomes 0, or it doesn't weight into what that stage of the iteration looks like during this autoregressive generation. So that's the main idea here. Set it very negatively. We can then pass that in to our softmax, and it's going to convert these into zeros, or non-impacting terms, things that don't have weight. So we're not paying attention to them because we couldn't be paying attention. Those tokens haven't been seen yet. With that said, I'm going to hand back over to Aveline. She's going to tie up the presentation with a little bit of results and conversation on the impact, along with some early adoption of transformers for other domains.
Yeah, so like James said, I will touch on the experimentations that the authors of the Attention is All You Need paper reported. They, similarly to the previous attention papers, their experimentations were based on text translation, so between English and German and English and French. For their experimentations, they reported 2 different metrics. One was a performance metric, and another one was the training cost required for training their models. What we see here is for the transformer models, the big model performs quite well on the blue score. It outperforms most of the other state-of-the-art models at the time. As for the training cost, what we notice here is that both the big and the base model have a lower training cost than the other state-of-the-art models. So the big model had a training cost that was about 10 to the 19, whereas all the other ones were as large as 10 to the, or as small as 10 to the 20. So this is a pretty revolutionary thing where we see an increase in performance, but we see a decrease in training cost. Now, this paper itself has been highly influential. Its citation count from this week at the end of March was 113,000 citations, and I'm sure that will change as time goes on. But the transformer architecture has been used as the basis for many state-of-the-art models. It is a fundamental backbone or building block for all LLMs that we know and use today, like GPT-4, Llama 2, Gemini. So in that sense, it's been quite revolutionary for AI tools and technologies that have really sort of emerged since this paper was published back in 2017. So as for early adoption, in other domains, in particular computer vision, we see the image transformer emerge in 2018. Now, they didn't use the transformer architecture directly, but they were inspired by this architecture on text and wanted to apply it on images. So the way that they used this idea was they positionally encode image pixels and then used a sort of local self-attention mechanism for different pixels in a query block to other pixels surrounding that query block making up a memory block. So it considers pixels in a local neighborhood around the query position. Nowadays, this methodology or process isn't heavily used. What people have found is that global attention in images is more effective, and it's just global attention is needed to acquire the results and the performance that we're looking for with these types of tools. And subsequent models that use this global attention have been found to be much more powerful. An example of this is the vision transformer, which does use the transformer architecture directly. In particular, they use the encoder for image classification. This is the original paper from 2020, which called an image is worth 16 by 16 words, transformers for image recognition at scale. Now, this is a whole field of study, but this was the original paper that I'm just going to briefly mention here. Like I said, they only use the vanilla transformer encoder. And what they do is they take an image, they splice this into different patches to produce a sort of sequence. Then they embed with positional encodings these patches into embedded and encoded sequences, and then pass this into the transformer encoder, add on an MLP head for classification, and build an image classifier that way. This was found to be very powerful, and like I said, lots has been built on top of this in recent years. All right, so that concludes our presentation. I hope you enjoyed all of this information about self-attention and transformers that we have presented here. Feel free to leave any comments or questions if you'd like.
Yeah, in the YouTube comments. We also have an additional slide just with a couple of discussion questions that I'm just going to put up here. We're not going to discuss this at length in our presentation or at all really, but just feel free to pause the video at this point and think about your understanding or how you've come to learn more about the transformer through our presentation. Additionally, if you have further questions, feel free to leave them in the comment section of this video. And if we have some time, I'd love to kind of start a discourse up there.